Tonight, we're going to explore something that will completely shatter how you see the cosmos. We're going to discover how empty the universe really is. And I'm not talking about there being a lot of space between stars. I'm talking about emptiness so profound, so complete, that it challenges our ability to comprehend it. Because here's what most people don't realize. When you look up at a night sky filled with stars, you're actually seeing one of the most elaborate illusions in nature. The universe isn't full, it's almost entirely nothing. And by the end of this journey, you're going to understand just how alone matter truly is in this vast cosmic ocean of emptiness. The numbers will genuinely astound you. Before we dive into this mind-bending exploration, if you find these kinds of deep journeys through space interesting, a quick like or subscribe would genuinely help this channel grow. It's a small thing for you, but it means everything to me. Now, make yourself comfortable. Let's begin. Let's start with something you do every single day without thinking about it. Right now, wherever you are, reach out and touch something solid. Maybe it's your desk. Maybe it's a wall. Maybe it's the arm of your chair. Feel that. Feel how real it is. How substantial. How undeniably there. That sensation of solidity is one of the most convincing experiences in your entire life. From the moment you were born, you've been learning that the world is full of stuff. Hard things and soft things, heavy things and light things, objects you can hold, surfaces you can stand on, walls you can lean against. The world feels packed with matter. And it's not just what you touch. Look around the room you're in right now. Count the objects. The furniture, the walls, the floor beneath you, the ceiling above. If you're outside, look at the trees, the buildings, the ground stretching to the horizon. Everywhere you look, there's something. Matter occupies space. Things exist. The world is full. Now wait until night falls. Step outside, away from the city lights if you can, and look up. What do you see? Stars. Thousands of them scattered across the darkness like diamonds on black velvet. If you're in a truly dark location, far from any artificial light, you can see the Milky Way itself. A river of light stretching from horizon to horizon, containing what appears to be countless stars, packed so closely together they blur into a luminous band. This creates an impression in your mind. A deeply held belief that feels so obviously true you've probably never questioned it. The impression that the universe is full, that space is crowded with stuff, that existence is dense with matter. From the atomic scale all the way up to the cosmic scale, this impression is an illusion, one of the greatest illusions in all of nature. That table you touched, it's almost entirely empty space. That rock you might pick up tomorrow, mostly nothing. The ground beneath your feet, overwhelmingly void. And those stars in the night sky, they're separated by distances so incomprehensibly vast that the space between them dwarfs their actual size by factors of millions upon millions. The universe isn't full. It's almost entirely empty. So empty that finding the right words to describe it becomes genuinely difficult. And understanding just how empty it really is requires us to start small and work our way up, scale by scale, until the full picture comes into focus. So let's begin at the smallest scale we can meaningfully comprehend: the atom. Everything you see around you, everything you touch, everything you've ever experienced in your physical life is made of atoms. The air you're breathing right now? Atoms. The water you'll drink today? Atoms. The screen or paper you're reading these words on? Atoms. Your own body, every cell, every organ, every thought generated by the neurons in your brain, all constructed from atoms. For most of human history, we thought atoms were solid, little spheres, like microscopic billiard balls packed together to form the matter we experience. The word atom itself comes from the ancient Greek word atomos, meaning uncuttable or indivisible. The Greek philosopher Democritus proposed around 400 BCE that if you kept cutting matter into smaller and smaller pieces, you would eventually reach a fundamental unit that couldn't be divided further. A solid, irreducible particle that was the basic building block of everything. This intuition persisted for over 2,000 years. Even when scientists in the 19th century began developing atomic theory in earnest, they imagined atoms as tiny, solid spheres. Different elements had different size spheres that combined in various ways to create molecules and materials. But the spheres themselves were solid, fundamental, full. Then came the early 20th century, and everything changed. In 1911, a physicist named Ernest Rutherford conducted one of the most famous experiments in the history of science. He fired tiny particles called alpha particles at a thin sheet of gold foil, expecting them to pass straight through with perhaps some minor deflection. After all, if atoms were solid spheres packed together, the alpha particles should bounce off or be absorbed. But that's not what happened. Most of the alpha particles passed straight through the gold foil as if it weren't even there. A small number deflected at various angles, and a very few, about 1 in 8,000, bounced straight back toward the source. Rutherford was stunned. He later said it was as if you fired a 15-inch artillery shell at a piece of tissue paper, and the shell came right back and hit you. The only explanation was that atoms weren't solid at all. They were mostly empty space, with a tiny, dense nucleus at the center where most of the mass was concentrated. This discovery shattered our understanding of matter. Atoms, the building blocks of everything, are almost entirely nothing. Here's how an atom actually works. At the center is the nucleus, containing protons and neutrons bound together by the strong nuclear force. This nucleus is incredibly small compared to the overall size of the atom. Surrounding the nucleus, at relatively enormous distances, are electrons. These electrons don't orbit the nucleus like planets around a sun, despite what some diagrams might suggest. Instead, they exist in probability clouds, regions of space where they might be found at any given moment. But the key point is the scale. The nucleus is tiny, the electron cloud is relatively huge, and between them, nothing. Complete emptiness. Let me give you a sense of the proportions involved. If you could somehow scale up an atom so that the nucleus was the size of a marble, about 1/2 inch across, the outer boundary of the atom where the electrons exist would be roughly 2 miles away. 2 miles. For a marble, picture this in your mind. You're standing in the center of a city, holding a marble in your hand. That marble represents the nucleus of an atom. Everything within 2 miles of where you're standing represents the atom itself. The buildings, the streets, the parks, the people, everything within that 2-mile radius is inside one atom. And between your marble and that 2-mile boundary, nothing. Empty space, no matter at all. The entire volume of the atom, minus that tiny marble you're holding, is void. Let me try another visualization. Imagine you place the nucleus, our marble, at the center of a football stadium, right on the 50-yard line. The electron cloud would be somewhere outside the stadium entirely. Maybe in the parking lot, maybe across the street, Everything between the marble on the 50-yard line and those distant electrons, the entire stadium, all those seats, the field, the scoreboards, everything would be empty space. This isn't an approximation or an exaggeration. This is what atoms actually are. The nucleus, which contains over 99.9% of the atom's mass, occupies only about 1/1,000,000th of the atom's volume. The rest is emptiness. So when you touch that table, when you feel its solidity, what's actually happening? Are you touching solid matter? No, you're not. What you're feeling is the electromagnetic force. The electrons in the atoms of your hand are repelling the electrons in the atoms of the table. These negatively charged particles push against each other, creating a force that your brain interprets as the sensation of touching something solid. But matter isn't actually contacting matter. Force is creating the illusion of contact. The atoms in your hand never actually touch the atoms in the table. They get close enough that their electromagnetic fields interact. And that interaction creates the feeling of solidity. But if you could zoom in far enough, you would see mostly empty space on both sides, with tiny nuclei and electron clouds that never quite meet. This has a startling implication. If you could somehow remove all the empty space from the atoms in your body, compressing just the nuclei together, you would shrink to a size smaller than a grain of sand. All the matter that makes you who you are, every molecule, every cell, every organ, would compress into something too small to see with the naked eye. Let me make this even more dramatic. If you removed all the empty space from all the atoms and all the humans on Earth, all 8 billion of us, the resulting matter would fit comfortably inside a single sugar cube. 8 billion people. Every thought anyone has ever had. Every love story, every tragedy, every triumph, every failure. All the matter that makes up all of humanity throughout history. One sugar cube. This is the first level of cosmic emptiness. Matter itself, the stuff that seems so solid and real, is almost entirely nothing. The atoms that make up everything are overwhelmingly empty space with tiny specks of matter scattered through them. But we're just getting started. Let's scale up from atoms to something larger. Let's consider planets. Earth feels substantial. It has a diameter of about 7,926 miles. When you stand on its surface, you feel gravity pulling you down, holding you firmly to what seems like an enormous ball of rock and metal and water. The planet stretches to the horizon in every direction. It feels massive, permanent, solid. But Earth is just a tiny sphere of matter floating in the vastness of space. And even Earth itself, as solid as it seems, is made of those mostly empty atoms we just discussed. At the atomic level, even our planet is more void than substance. But let's set aside the atomic emptiness for now and just look at the empty space around Earth. Let's start with our nearest neighbor, the Moon. The Moon orbits Earth at an average distance of about 238,855 miles. That number might sound abstract, so let me put it in perspective. You could fit all the other planets in our solar system lined up side by side in the gap between Earth and the Moon. Jupiter, Saturn, Uranus, Neptune, Mars, Venus, Mercury, all 7 of them would fit in that empty space with room to spare. Most people are genuinely surprised by this fact. When you see pictures of the Earth-Moon system, whether in textbooks or on websites or in movies, the Moon is almost always shown much closer than it actually is. Artists and filmmakers do this because showing the true distance would make the Moon look like a tiny dot far in the distance, which doesn't make for an interesting or visually appealing image. But that gap, those 238,000 plus miles between us and our nearest cosmic neighbor, is just empty space. There's nothing there. No matter, no atmosphere, no anything. Just void. And here's the remarkable thing. The moon is close. It's the closest natural object to Earth in the entire universe. It's so close that humans have actually visited it. 12 people have walked on its surface. We've sent robots there. We can see it with our naked eyes every night. By cosmic standards, the moon is practically touching us, and yet, the space between us and this closest neighbor could swallow every other planet in the solar system. Now, let's zoom out further. Let's consider the entire solar system. The sun dominates our solar system. It contains 99.86% of all the mass in the solar system. Everything else, every planet, every moon, every asteroid, every comet, every grain of dust, makes up only 0.14% of the total. The sun is so massive that everything else is almost a rounding error. The sun has a diameter of about 864,000 miles. That's enormous by any human standard. You could fit about 109 Earths across the sun's diameter. About 1.3 million Earths could fit inside. The sun's volume. It's a gigantic ball of hydrogen and helium undergoing nuclear fusion, converting 4 million tons of matter into pure energy every single second. Earth orbits this massive star at a distance of about 93 million miles. We call this distance 1 astronomical unit, and it's so vast that light, traveling at 186,000 miles per second, takes about 8 minutes and 20 seconds to cross it. Think about that. Light is the fastest thing in the universe. Nothing can travel faster. And yet, light from the sun takes over 8 minutes to reach Earth. If the sun suddenly vanished right now, we wouldn't know for another 8 minutes and 20 seconds because the last light it emitted would still be traveling toward us. Let me put the Earth-Sun distance in perspective with a scale model. This is one of the most effective ways to grasp the emptiness of the solar system. Shrink the sun down to the size of a basketball. A standard basketball is about 9.5 inches in diameter. In this scale model, how big would Earth be, and how far away? Earth would be about the size of a small peppercorn. Those little black spheres you grind onto your food. Tiny. Almost insignificant compared to the basketball sun. And the distance? That peppercorn would be located about 98 feet away from the basketball. 98 feet. That's roughly the length of a basketball court. Picture it. The sun is a basketball sitting at one end of a basketball court. Earth is a peppercorn at the other end. And between them, nothing. Complete emptiness across the entire length of the court. Let's continue building our scale model by adding the other planets. Mercury, the closest planet to the sun, would be even smaller than the peppercorn, like a grain of sand. Located about 38 feet from our basketball sun. Venus would be another peppercorn-sized object, about 72 feet away. Mars, smaller than Earth, would be a slightly smaller peppercorn roughly 150 feet from the sun. We're already well beyond our basketball court. Jupiter, the largest planet in our solar system, would be about the size of a large marble in this model. It would be located about 510 feet from the basketball sun. That's about the length of 1.5 football fields. Between Jupiter and the inner planets, almost nothing. Just empty space. Saturn, with its famous rings, would be another large marble, positioned about 940 feet from the Sun. That's more than 3 football fields away. The space between Saturn and Jupiter? Empty. Uranus would be a small marble about 1,900 feet away, more than a third of a mile from our basketball sun. Neptune would be a similar small marble at roughly 3,000 feet, over half a mile away. And Pluto, out in the Kuiper Belt, would be a tiny speck about 4,000 feet from our basketball sun, roughly 3/4 of a mile away. So let's step back and look at what we've built. In this scale model, with the sun as a basketball, the entire solar system from the sun to Pluto spans about 3/4 of a mile. And within that 3/4 of a mile, how much actual matter is there? A basketball, a few marbles, a couple of peppercorns, and some specks of dust. That's it. The rest is empty space. If you tried to calculate what percentage of the solar system's volume is occupied by matter, the number would be so small, it would be almost meaningless. We're talking about fractions of a percent so tiny they approach zero. The solar system is overwhelmingly, almost entirely, nothing at all. But wait, we're not finished with the solar system yet, because it extends far beyond Pluto. Beyond the Kuiper Belt, where Pluto and other dwarf planets reside, lies an even more distant region called the Oort cloud. This is a vast spherical shell of icy objects that marks the true outer boundary of the Sun's gravitational influence. The Oort cloud is believed to begin at about 2,000 astronomical units from the Sun, where, remember, 1 astronomical unit is the distance from Earth to the Sun. It extends outward to perhaps 100,000 astronomical units. How far is that? 100,000 astronomical units is roughly 1.5 light years. The Oort cloud is so distant that light from the Sun, traveling at 186,000 miles per second, takes over a year to reach its outer edge. Let's add this to our scale model. If the Sun is a basketball in New York City, where would the outer edge of the Oort cloud be? About 6,000 miles away, roughly the distance from New York to Tokyo. So the solar system in our basketball scale model spans from a basketball in New York to an invisible boundary somewhere near Tokyo. And within that enormous distance, the matter consists of 1 basketball, a few marbles, some peppercorns, and scattered specks of dust, most of which would be concentrated within the first 3/4 of a mile. The Oort cloud itself is almost entirely empty. It's thought to contain perhaps trillions of icy objects, but these objects are separated by millions of miles from each other. If you flew through the Oort cloud in a spacecraft, you would likely never see a single object with your naked eye. The emptiness is that complete. So when we include the Oort cloud, the solar system is a region of space spanning about 2 light years in diameter. 2 light years is about 11.76 trillion miles. And within that inconceivable volume, the total amount of matter is essentially the Sun, 8 planets, some moons, and scattered debris. The Sun contains 99.86% of all that matter. And even the Sun, massive as it is a tiny object compared to the space it occupies. Let me try one more way to make this concrete. Imagine the solar system as a sphere 2 light years in diameter. Now imagine somehow compressing all the matter in that sphere, every planet, every moon, every asteroid, every comet, every particle of dust, everything, into a single ball. That ball, containing all the matter of the solar system, would be about 864,000 miles across, the size of the Sun. But the volume of a sphere 2 light years in diameter is absolutely staggering. The Sun, even though it contains almost all the matter in the solar system, occupies only about 0.0000000000000000000000001% of that volume. I could keep adding zeros, but you get the point. The solar system is almost entirely empty space. The matter within it, as impressive as it seems from our tiny perspective on Earth, is essentially nothing compared to the void that surrounds it. This is starting to give you a sense of what we're dealing with, but we've only just begun our journey outward, because now we need to zoom out from the solar system and examine the space between stars. Our nearest stellar neighbor is Proxima Centauri, a small red dwarf star that's part of the Alpha Centauri triple star system. Proxima Centauri is about 4.24 light years away from us. A light year is the distance light travels in 1 year. Light moves at about 186,000 miles per second. So in 1 year, it covers roughly 5.88 trillion miles. So Proxima Centauri is approximately 25 trillion miles from Earth. 25 trillion miles. That number is so large it's almost meaningless. Let me try to make it tangible. Remember our scale model where the Sun was a basketball? Let's go back to that. In our basketball solar system model, with the Sun as a basketball and Earth as a peppercorn 98 feet away, where would Proxima Centauri be? About 5,200 miles away. 5,200 miles. That's roughly the distance from New York to London. In our scale model, the Sun is a basketball sitting in New York City, and the nearest star, Proxima Centauri, is another ball. Smaller than a golf ball because it's a red dwarf sitting somewhere in London. And between them, absolutely nothing. Complete, total perfect emptiness, spanning 5,200 miles. In this model, where would all the planets be? Where would the Oort cloud end? They would all be within about 3/4 of a mile of the basketball Sun. You could fit every planet, every moon, every significant object in our entire solar system within a small neighborhood in New York. And then there would be 5,200 miles of pure nothing before you reach the next tiny ball in London. This is the reality of space between stars. The distances are so vast, the emptiness so complete that the matter itself seems almost incidental. Stars are like isolated specks of dust, separated by enormous gulfs of void. Within the Milky Way galaxy, there are estimated to be between 100 billion and 400 billion stars. That sounds like an unimaginably large number. And it is large, but the Milky Way is also about 100,000 light years across. Let's think about the average distance between stars in our galaxy. Near the galactic center, where stars are more densely packed, stars might be separated by about half a light year on average. That's still trillions of miles of emptiness between neighboring stars. In the outer regions of the galaxy, where our Sun is located, the average distance between stars is about 4 to 5 light years. That's roughly the distance to Proxima Centauri. This means that even in a galaxy containing hundreds of billions of stars, those stars are incredibly far apart. If you picked a random point anywhere within the Milky Way, you would almost certainly find yourself in empty space. The chance of being inside a star, or even close to one, is infinitesimally small. The Milky Way, despite containing more stars than you could count in several lifetimes, is mostly nothing. The stars within it, as numerous as they are tiny specks separated by vast, dark gulfs of emptiness. And here's something else to consider. the space between stars isn't completely empty. There's something called the interstellar medium, gas and dust scattered through the void between stars. But this interstellar medium is incredibly thin, almost unbelievably thin. On average, there's about 1 atom per cubic centimeter in the interstellar medium. 1 atom per cubic centimeter. Let me help you understand how empty that is. The air you're breathing right now, ordinary sea level atmosphere, contains about 2.7 times 10 to the 19th power molecules per cubic centimeter. That's written out as 27 billion molecules in every cubic centimeter of air. The interstellar medium has 1 atom in that same volume. The best vacuum chambers we can create on Earth, using the most sophisticated technology available, can achieve pressures down to about 100,000 molecules per cubic centimeter. Scientists call this an ultra-high vacuum. It's considered incredibly empty by laboratory standards. These vacuums are used for sensitive scientific instruments and manufacturing processes where even trace amounts of matter would cause problems. The interstellar medium is about 100,000 times emptier than the best vacuum we can create. Space between stars isn't just empty. It's emptier than anything humans have ever been able to create artificially. It's emptier than anything in our everyday experience could prepare us for. When we say space is a vacuum, we're actually understating the case. Space is beyond vacuum. It's closer to true nothingness than anything else we know of. And yet, remarkably, we've only scratched the surface of cosmic emptiness. So far, we've been exploring the space within our galaxy. The Milky Way, vast as it is just one galaxy among trillions. And the space between galaxies makes the space between stars look positively crowded. The voids between galaxies, and the even larger structures that organize matter on cosmic scales, reveal emptiness that defies human comprehension. We're going to explore these in the sections ahead. But for now, let's pause and absorb what we've learned. At every scale we've examined, emptiness dominates. Atoms, over 99.9999999999999% empty space. The solar system, almost entirely void, with matter occupying a fraction of a percent so small, it approaches zero. The space between stars, emptier than any vacuum we can create, with single atoms scattered across cubic centimeters of nothing. Matter is the exception, not the rule. The universe isn't sprinkled with stuff like salt on a table. It's more like a few grains of salt scattered across an entire continent. And even those grains, when you look closely, are themselves mostly empty space. This is the first great truth about cosmic emptiness. It exists at every scale we examine. From the smallest building blocks of matter to the vast distances between stars, void dominates. And as we continue our journey outward, zooming out to ever larger scales, this pattern doesn't change. It only becomes more extreme. The illusion of fullness that your daily experience creates, the solid table, the countless stars, the matter-filled world, is exactly that. An illusion. A trick of perception created by forces and light, and the limitations of human senses. The reality is emptiness. Profound, overwhelming, almost incomprehensible emptiness. And we're only beginning to understand just how empty it really is. Now that we understand how empty our immediate cosmic neighborhood is, let's zoom out even further. Because everything we've explored so far, the emptiness within atoms, the void of the solar system, the vast distances between stars, all of that is just the beginning. The space between stars, as incomprehensibly vast as it is nothing compared to the emptiness between galaxies. And the emptiness between galaxies is nothing compared to the cosmic voids that dominate the large-scale structure of the universe. We're about to enter a realm of emptiness so profound that it will challenge your ability to conceptualize it. But let's take it step by step, starting with the deeper look at our own galaxy. The Milky Way is a barred spiral galaxy. When astronomers look at it from outside, which we can only do through computer models since we're embedded within it, they see a magnificent structure. A central bar of stars surrounded by sweeping spiral arms, the whole thing rotating slowly around a common center. It's beautiful, it's vast, and it's almost entirely nothing. The Milky Way stretches roughly 100,000 light years from one edge to the other. The disk where most stars reside is about 1,000 light years thick. At the center sits a bulge of older, yellowish stars, surrounding a supermassive black hole called Sagittarius A star. This black hole has a mass of about 4 million times our Sun. Yet it's invisible to the naked eye because black holes don't emit light. We only know it's there because of the way stars orbit around it, whipping around an invisible point at tremendous speeds. Within this grand structure, there are somewhere between 100 billion and 400 billion stars. Let's split the difference and call it 200 billion. That's 200 billion points of light scattered through at a disk 100,000 light years across. 200 billion sounds like an enormous number, and it is. If you tried to count to 200 billion, counting one number per second without stopping to eat or sleep, it would take you over 6,300 years. You'd have started counting during the construction of Stonehenge and still not be finished today. But here's the paradox. Even with 200 billion stars, the Milky Way is almost entirely empty space. Those stars, numerous as they are, occupy only a vanishingly small fraction of the galaxy's volume. Let me show you the mathematics of this emptiness. The Sun has a diameter of about 864,000 miles. Proxima Centauri, our nearest stellar neighbor, is about 25 trillion miles away. That means the distance to the nearest star is approximately 29 million times the diameter of the Sun itself. Think about that ratio, 29 million to 1. The emptiness between stars is 29 million times larger than the stars themselves. Let me make this more concrete with another scale model. Imagine you have a marble about half an inch in diameter representing the Sun. To reach another marble representing Proxima Centauri, the nearest star, you would need to travel about 228 miles. 228 miles of emptiness for every half inch of matter. Now multiply this by 200 billion stars, each separated by similar enormous distances, and you begin to grasp the true nature of a galaxy. A galaxy is not really a collection of stars. It's a collection of emptiness, occasionally interrupted by tiny isolated specks of matter. If you could somehow remove all the empty space from the Milky Way, compressing just the matter together, the result would be shockingly small. All the stars, all the planets, all the gas and dust, all the dark matter, everything would compress into something that, while tremendously massive, would occupy only a minuscule fraction of the galaxy's current volume. Let me walk through the calculation because the numbers are staggering. The visible matter in the Milky Way, meaning the stars, gas, and dust we can actually detect, totals roughly 100 billion solar masses. If we packed all this matter at the density of the Sun, which is Already a fairly dense object by cosmic standards, it would occupy a volume of about 100 billion times the Sun's volume. That sounds like a lot. 100 billion suns worth of volume. But let's compare it to the actual volume of the Milky Way. The Milky Way, as a disk 100,000 light-years across and 1,000 light-years thick, has a volume of approximately 8 times 10 to the 66th power cubic kilometers. That's an 8, followed by 66 zeros. The matter within the galaxy, if compressed to solar density, would occupy roughly 10 to the 29th power cubic kilometers. That's a 1, followed by 29 zeros. The ratio between these numbers is about 10 to the 37th power. In other words, the Milky Way is roughly 10 trillion parts emptiness for every 1 part matter. In percentage terms, the Milky Way is approximately 99.9999999999999999999999999% empty space. Each of those nines represents a real decimal place in the actual calculation. This is not hyperbole. This is the mathematical reality of our galaxy. You live in a galaxy that is essentially nothing at all, with occasional specks of something scattered through it at enormous intervals. But here's what makes this even more remarkable. The Milky Way, as empty as it is actually one of the denser regions of the universe. Galaxies are where matter congregates. They're the cosmic cities, the places where stuff gathers together. The space between galaxies makes our already empty galaxy look positively crowded. Let me introduce you to intergalactic space. The Milky Way is part of a collection of galaxies called the Local Group. This is our cosmic neighborhood, containing about 50 galaxies bound together by their mutual gravitational attraction. The two dominant members are the Milky Way and Andromeda. Most of the others are small dwarf galaxies, collections of a few billion stars or less that orbit around the two big spirals like satellites. Andromeda, our nearest large galactic neighbor, is about 2.5 million light-years away. Let's pause on that number. 2.5 million light-years. Light, traveling at 186,000 miles per second, takes 2.5 million years to cross the distance between us and Andromeda. When the light now reaching our telescopes from Andromeda began its journey, our human ancestors hadn't yet evolved. Homo habilis, one of our earliest ancestors capable of making stone tools, wouldn't appear for another 300,000 years. That light has been traveling through space since before humans existed, and it's coming from our nearest major galactic neighbor, the closest one. To put this distance in perspective, 2.5 million light-years is about 25 times the diameter of the Milky Way itself. If our galaxy were a frisbee about 10 inches across, Andromeda would be another frisbee roughly 20 feet away. And between those two frisbees, between the Milky Way and Andromeda, nothing but the near-perfect vacuum of intergalactic space. The intergalactic medium is the space between galaxies, and it's emptier than anything we've discussed so far. While the interstellar medium within our galaxy contains about 1 atom per cubic centimeter, the intergalactic medium contains about 1 atom per cubic meter. 1 atom per cubic meter. That's roughly 1 million times emptier than the already incredibly empty interstellar space. The intergalactic medium makes the space between stars look dense by comparison. It's so empty that if you tried to create such a perfect vacuum in a laboratory on Earth, you couldn't do it. Our best vacuum technology can't come close to replicating the emptiness that exists naturally between galaxies. If you were somehow floating in intergalactic space, far from any galaxy, you would experience a loneliness beyond human comprehension. The nearest atom to you might be a meter away. The nearest star might be millions of light years distant. You would be surrounded by a darkness so complete and an emptiness so perfect that the void would seem almost tangible. You would be, in the most literal sense possible, alone. The local group, with its 50 galaxies scattered across about 10 million light years, is actually a relatively cozy neighborhood by cosmic standards. There are other galaxies nearby, even if nearby means millions of light years. You can look up and see Andromeda on a dark night. The universe, from our vantage point, seems populated. But when we zoom out further, we discover something unsettling. The local group sits near the edge of a much larger structure called the Virgo supercluster. And the Virgo supercluster itself is part of an even larger structure called Laniakea, a supercluster of superclusters containing about 100,000 galaxies spread across 520 million light years. These structures, massive as they are, represent the relatively dense regions of the universe, the filaments where matter has congregated over billions of years of cosmic evolution. Between these filaments lie the true deserts of the cosmos, cosmic voids. Let me introduce you to the Boötes Void, one of the most famous and haunting empty regions in the known universe. The Boötes Void was discovered in 1981 by astronomer Robert Kirshner and his colleagues. They were conducting a survey of galaxies in the direction of the constellation Boötes, mapping out where galaxies were located in three-dimensional space. What they found, or rather what they didn't find, shocked the astronomical community. There was a region of space, centered about 250 million light years from Earth, that contained almost nothing. A sphere of emptiness roughly 330 million light years in diameter. 330 million light years. To cross this void, light would need 330 million years. When light, now arriving at one side of the Boötes Void, began its journey from the other side, multicellular life on Earth was just beginning to appear. The Cambrian explosion hadn't happened yet. The dinosaurs wouldn't evolve for another 100 million years after that. Humans wouldn't exist for another 329 million years. The Boötes Void is over 3,000 times wider than our entire Milky Way galaxy. If you place the Milky Way in the center of the Boötes Void, you could fit over 3,000 Milky Ways across its diameter. Over 36 billion Milky Ways could fit inside its volume. And within this incomprehensible space, how many galaxies did astronomers find? About 60. 60 galaxies, scattered through a volume that could contain 36 billion Milky Ways. That's roughly one galaxy for every 600 million potential Milky Way volumes. To understand just how empty this is, let's compare it to the local group. Our local group is about 10 million light years across and contains about 50 galaxies. If the Boötes Void had the same density of galaxies as the local group, it would contain approximately 1.8 quadrillion galaxies. It contains 60. The Boötes Void is roughly 30 million times emptier than our already sparse local group. It's emptiness on a scale that words struggle to convey. Astronomer Greg Aldering once made an observation about the Boötes Void that's worth repeating. He pointed out that if the Milky Way had been located at the center of the Boötes Void, instead of where it actually is, human astronomers wouldn't have known that other galaxies existed until the 1960s. Think about what that means. Edwin Hubble discovered that Andromeda was a separate galaxy in the 1920s. Before that, astronomers thought the fuzzy spiral nebulae they observed were clouds of gas within our own galaxy. The realization that the universe extended far beyond the Milky Way was one of the most profound discoveries in human history. But if we had been born in the Botas void, we might still think we're alone. The nearest galaxies would be so distant, so faint, that only the most powerful modern telescopes could detect them. For all of human history until perhaps 50 years ago, we would have looked up at the night sky and seen only our own galaxy. We would have believed, with good reason, that the Milky Way was the entire universe. The loneliness of such an existence is hard to fathom. On a planet within the Botas void, your night sky would be strange and melancholy. You would see the stars of your own galaxy, yes, but beyond that, in almost every direction, nothing. No sister galaxies visible to the naked eye. No neighboring spiral arms catching the light. Just darkness stretching outward, forever, with perhaps a few impossibly faint smudges, visible only through the most powerful instruments. Civilizations in the Botas void would develop a very different understanding of the cosmos than we have. They would think of themselves as truly alone in the universe, and in a practical sense they would be right. But the Botas void, enormous as it is, isn't even the largest empty region we've discovered. There's the KBC void, named after astronomers Ryan Keenan, Amy Barger, and Lennox Cowie, who mapped it extensively. The KBC void is roughly 2 billion light years in diameter. That's about 6 times larger than the Botas void. 2 billion light years across. Light crossing that void would need 2 billion years to complete the journey. When that light began traveling, the most complex life on Earth was single-celled organisms. Multicellular life hadn't appeared yet. The entire history of complex life on Earth, from the first animals to fish, to dinosaurs, to mammals, to humans, has occurred in less time than it takes light to cross the KBC void. The KBC void isn't completely empty. It has a density of galaxies about 20% lower than the cosmic average. But here's something fascinating. Our own Milky Way appears to be located near the edge of the KBC void. We're not in the densest part of the universe, we're actually in a relatively sparse region, living near one of the larger underdense areas in our cosmic neighborhood. There's also the giant void, sometimes called the Canes Venatici supervoid, approximately 1 billion light years across. And then there's the CMB cold spot, a mysterious region detected in the cosmic microwave background radiation that might correspond to an enormous supervoid, though astronomers are still debating its exact nature and size. These voids aren't completely empty. They contain some galaxies, scattered thin and lonely across the darkness. But compared to the dense filaments and clusters where most galaxies congregate, voids are almost devoid of matter. They're the true deserts of the cosmos, empty expanses where nothing much happens and nothing much exists. When astronomers map the distribution of galaxies across the observable universe, voids turn out to be the dominant feature. Let me repeat that because it's crucial. Voids are the dominant feature. About 80% of the universe's volume is occupied by voids. Only about 20% contains the filaments, walls, and clusters where galaxies gather. 80% emptiness. The universe is 4/5 nothing, interrupted only occasionally by thin threads and scattered clumps of something. And here's what makes this even more remarkable. Remember what we established earlier? Galaxies themselves are almost entirely empty space. Stars within galaxies are separated by light years of void, and the atoms that make up those stars are themselves overwhelmingly empty. So when we say that 80% of the universe is void, we're not saying 80% is empty and 20% is full. We're saying 80% is extraordinarily empty and 20% is merely extremely empty. The difference between voids and filaments is relative. The universe is empty everywhere. Some places are just emptier than others. It's emptiness all the way down. Let me try to convey the scale of cosmic voids through comparison, though I'll warn you that human language starts to fail at these scales. Imagine you're standing in the Sahara Desert. It's vast, hot, silent. You could walk for days without seeing another person. The Sahara covers about 3.5 million square miles. It feels like one of the emptiest places on Earth. Now, imagine that the entire Sahara Desert is a single atom. One of those atoms that, as we discussed in part 1, is itself almost entirely empty space. If we scaled up a cosmic void to maintain the same proportional relationship, that void would be larger than the observable universe itself. That comparison doesn't make intuitive sense. The scale difference is so extreme that our normal frameworks for understanding relationships break down. We're comparing something the size of a desert to something spanning hundreds of millions of light years. The ratio between them exceeds human comprehension. Let me try another approach. Consider time. Light travels at about 186,000 miles per second. In 1 year, it covers approximately 5.88 trillion miles. That distance, 1 light year, is already so large that humans have no experiential basis for understanding it. You can't visualize 5.88 trillion miles. Your brain simply refuses to process it meaningfully. The Bota's void is 330 million light years across. Light needs 330 million years to traverse it. 330 million years ago, the supercontinent Pangaea hadn't yet formed. The dominant life forms on Earth were early amphibians and primitive reptiles. The Atlantic Ocean didn't exist. The Appalachian Mountains, among the oldest mountain ranges on Earth, were still being pushed up by tectonic forces. All of human history, from the first cave paintings, to the construction of the pyramids, to the rise and fall of Rome, to the Renaissance, to the Industrial Revolution, to the moon landing to this very moment, all of it is a rounding error compared to the time it takes light to cross the Bota's void. And that light was traveling through almost nothing the entire time, crossing empty space, passing through a void where galaxies are so rare that if you picked a random point within it, the nearest galaxy might be millions of light years away. This is the nature of the universe at the largest scales. It's not sprinkled with matter the way stars seem sprinkled across the night sky. That appearance is an illusion created by our particular vantage point within a galaxy, within a filament. The reality is that matter is organized into vast structures separated by even vaster emptiness. The universe is like a sponge, except the holes in the sponge are far larger than the material. Imagine a sponge that's 99.99% holes and only 0.01% actual sponge material. That's closer to the reality of cosmic structure, though even that analogy understates the emptiness. Or think of it like soap bubbles floating in air. The bubbles themselves are the voids, nearly empty. The thin films where bubbles meet, those fragile surfaces of soap and water, are the filaments where galaxies cluster. Most of the volume is bubble. Most of the universe is void. This brings us to one of the most profound realizations about our cosmic situation. When you look up at the night sky and see thousands of stars scattered across the darkness, you're seeing one of the densest regions in the local universe. You're not looking at a representative sample of what the cosmos contains. You're looking at a cosmic city from inside its downtown district. You're embedded within a galaxy, the Milky Way, which is itself embedded within a local group of galaxies, which is part of the Virgo supercluster, which is part of the Laniakea supercluster. By cosmic standards, you live in a crowded neighborhood, a place where matter has congregated, a place where things exist. If you could somehow teleport to a truly random location in the universe, the overwhelming odds are that you would find yourself in a void, far from any galaxy, far from any star, far from any planet or moon or asteroid, surrounded by the most perfect emptiness imaginable, emptiness so complete that the nearest atom might be light years away. The stars you see at night are the exception, not the rule. The night sky creates a profound illusion of cosmic fullness. The reality is almost exactly the opposite, and this emptiness has been growing. It's not static. The universe is expanding, and that expansion is accelerating. Every day, the voids get a little larger. The filaments get a little more stretched. The distances between galaxy clusters increase. Dark energy, the mysterious force driving this acceleration, is pushing the universe apart at an ever-increasing rate. The emptiness that dominates today will be even more dominant tomorrow, and more so the day after that, continuing for billions upon billions of years into the future. Billions of years from now, the cosmic voids will be far larger than they are today. The distances between isolated galaxy clusters will have grown so immense that light from one cluster will never be able to reach another. The observable universe will shrink for any observers living in that distant epoch. They will look out at the cosmos and see only their own local group of galaxies, perhaps merged by then into a single, large elliptical galaxy surrounded by infinite darkness. The universe will keep expanding, the matter will keep spreading out, the emptiness will keep winning. Eventually, in the extremely far future, even atoms will be affected. Some theories suggest that if the expansion continues to accelerate, space will eventually expand so rapidly that it will tear apart galaxies, then solar systems, then planets, then atoms themselves. This hypothetical fate is called the Big Rip, and while it remains speculative, it represents the logical extreme of a universe where emptiness is destiny. Even without the Big Rip, the far future is bleak in terms of cosmic content. Stars will eventually burn out. New stars will stop forming as galaxies exhaust their supplies of hydrogen gas. The universe will grow dark, cold, and empty. The matter that seems so prevalent from our privileged position will reveal itself to be the temporary exception it always was. Emptiness is not just the current state of the cosmos, it's the direction the cosmos is heading. The ultimate fate of the universe is maximum emptiness, as close to absolute. Nothing as existence can approach while still technically being something. This is the trajectory of everything. The universe began in an incredibly hot, dense state during the Big Bang, when matter and energy were packed together in unimaginable concentrations. Since then, it has been spreading out and cooling. The emptiness between matter has been growing for 13.8 billion years and will continue to grow for trillions of years more. We happen to live at a relatively special time, cosmically speaking. A time when stars still shine, when galaxies are still visible across the void, when the universe still has structure that can be observed and mapped. future civilizations, if any exist in the distant epochs to come, will not be so fortunate. They will inherit a darker, lonelier, emptier cosmos. The universe's destiny is emptiness. And looking at the numbers, looking at the voids that already dominate the cosmic landscape, looking at the acceleration of expansion, one could argue that the universe is already most of the way there. The night sky lies to us. It shows us stars, suggests fullness, implies a cosmos rich with matter. But the truth is that we live in a universe that is overwhelmingly, fundamentally, profoundly empty. A universe where matter is the rare exception and void is the eternal rule. And as vast as the emptiness is today, it will be vaster tomorrow. The darkness between galaxies will grow. The voids will expand. The thin filaments of matter will stretch and disperse. In the cosmic long run, emptiness always wins. Now that we've explored the profound emptiness of cosmic voids, the vast deserts between galaxies, and the lonely expanses where almost nothing exists, let's turn our attention to something that might seem contradictory: structure. Because while the universe is overwhelmingly empty, the matter that does exist isn't scattered randomly like dust thrown into the wind. It's organized, arranged, patterned. Matter in the universe has assembled itself into an intricate architecture called the cosmic web. A vast, three-dimensional network of filaments, walls, and nodes that stretches across the entire observable universe. And understanding this structure reveals something remarkable about the cosmos. Even in its overwhelming emptiness, there's order, there's pattern, there's a shape to reality. Let's start with how astronomers discovered that the universe had any large-scale structure at all. Because for most of human history, we had no idea. For thousands of years, humans looked up at the night sky and saw points of light scattered across darkness. We mapped constellations, tracked the movements of planets, studied the phases of the moon. But the idea that there might be a pattern to how things were distributed in the deep universe, that concept simply didn't exist. When we first realized that the fuzzy nebulae in our telescopes were actually other galaxies, island universes far beyond our own Milky Way, we assumed they were scattered more or less randomly throughout space. The universe, we thought, was like a vast ocean with galaxies floating through it in no particular arrangement. Some areas might have a few more galaxies, some a few less, but there was no overall structure, no grand pattern. This assumption seemed reasonable. When you look at the night sky, stars appear randomly distributed. Why should galaxies be any different? The universe, we imagined, was uniform on large scales, the same everywhere. No special arrangements, no grand architecture. Then, in the late 1970s and early 1980s, astronomers began a project that would revolutionize our understanding of the cosmos. They started creating three-dimensional maps of galaxy positions. The key innovation was this. Astronomers had long known where galaxies appeared in the sky, their positions relative to other objects. But position on the sky is only two-dimensional. To understand how galaxies were truly distributed, you needed to know the third dimension: distance. Using a phenomenon called redshift, astronomers could measure how far away each galaxy was. When a galaxy moves away from us, the light it emits gets stretched to longer wavelengths, shifting toward the red end of the spectrum. The faster it's moving away, the more the light is stretched. And because the universe is expanding, more distant galaxies are moving away faster. By measuring how much a galaxy's light was redshifted, astronomers could calculate its distance. By combining position on the sky with distance, researchers could build up a three-dimensional picture of how galaxies were distributed in space. They could see, for the first time, the actual architecture of the cosmos. What they found shocked everyone. Galaxies weren't randomly distributed at all. They formed patterns, long chains of galaxies stretched across hundreds of millions of light years. Vast sheets and walls of galaxies surrounded enormous empty regions. The universe had structure on scales far larger than anyone had imagined. In 1989, astronomers Margaret Geller and John Huchra published one of the most famous maps in the history of cosmology. They had surveyed a slice of the nearby universe, measuring the positions and distances of thousands of galaxies. When they plotted the results, the pattern was unmistakable. Galaxies weren't scattered like sand on a beach. They were arranged like the walls of soap bubbles. Thin surfaces of galaxies surrounded huge, nearly empty voids. The universe had a foam-like structure, with bubbles of emptiness enclosed by delicate membranes of matter. One particularly prominent feature in their map was a vast sheet of galaxies stretching across the sky. They called it the Great Wall. This structure was about 500 million light-years long, 300 million light-years wide, and only about 15 million light-years thick. A cosmic pancake of galaxies, spanning distances that dwarfed anything astronomers had previously identified. This was the first clear evidence of what we now call the cosmic web. The universe had architecture. Matter had organized itself into a pattern that extended across billions of light years. Since that pioneering work, ever more detailed surveys have mapped larger and larger portions of the universe. The 2-degree field galaxy redshift survey in the late 1990s measured positions for over 200,000 galaxies. The Sloan Digital Sky Survey, which began in 2000 and continues today, has mapped the positions of millions of galaxies across billions of light years. The resulting maps are breathtaking. They show the cosmic web in exquisite detail. Filaments and walls and clusters and voids extending as far as our telescopes can see. The universe has revealed its hidden structure, and that structure is both beautiful and strange. So what exactly is this cosmic web? What are its components? How is it organized? At the largest scales, matter in the universe is arranged into 3 basic types of structures: filaments, walls, and nodes. Understanding each of these is essential to grasping the architecture of emptiness. Filaments are long, thread-like structures where galaxies congregate. Imagine strings stretching across vast distances, and along those strings, galaxies are gathered like beads on a necklace. These filaments can extend for hundreds of millions of light years, connecting distant regions of space with bridges of matter. The filaments aren't solid, of course. Nothing at cosmic scales is solid in the way we experience solidity. They're simply regions where the density of galaxies is higher than average. If you could fly through a filament, you would still experience mostly emptiness. But compared to the voids on either side, filaments are crowded places. Think of a filament as a cosmic highway, channeling matter from the empty voids into the denser regions where clusters form. Galaxies flow along these filaments, slowly falling towards the massive concentrations at the intersections. The filaments are the arteries of the cosmic web, the channels through which the universe's sparse matter circulates. Walls are similar to filaments, but flatter. They're sheet-like structures where galaxies cluster, forming 2-dimensional surfaces in three-dimensional space. The Great Wall, discovered by Geller and Hucre, is an example. Walls often form the boundaries between voids, like the membranes of soap bubbles separating one pocket of emptiness from another. If filaments are the threads of the cosmic web, walls are the fabrics. Thin sheets of galaxies stretching across millions of light years, defining the edges of the universe's great empty spaces. Walls and filaments together create a skeleton, a framework around which the cosmos is organized. Nodes are the points where multiple filaments intersect. These are the cosmic crossroads, the places where several highways of matter meet. At these intersections, matter is most concentrated. Galaxy clusters, the largest gravitationally bound structures in the universe, form at these nodes. A galaxy cluster can contain thousands of individual galaxies, all bound together by gravity into a single enormous system. The galaxies within a cluster orbit their common center of mass, held together despite the expansion of the universe by their combined gravitational pull. Between the galaxies, enormous amounts of hot gas fill the cluster, heated to millions of degrees by the violent formation process. These clusters sit at the nodes of the cosmic web, like cities at the intersections of major highways. They're the densest concentrations of matter in the universe, the places where the most stuff has accumulated. And yet, even these dense clusters are mostly empty space. The galaxies within them are still separated by millions of light years, and those galaxies themselves are overwhelmingly void. And between all these structures surrounding the filaments and walls, filling the spaces between the nodes, are the voids we explored in the previous section. Vast, nearly empty regions that occupy about 80% of the universe's total volume. The overall pattern resembles foam or sponge. The bubbles of a foam are the voids, nearly empty. The thin films where bubbles meet are the filaments and walls. And where many films converge, where multiple bubbles come together at corners, you find the dense clusters. Picture the universe as an enormous block of foam stretching in every direction. Most of it is bubble, is void, is nothing. Only the thin membrane separating the bubbles contains significant matter. And even that membrane is incredibly sparse by any standard we would recognize from daily life. This structure didn't form randomly. It emerged from the conditions of the very early universe through the patient action of gravity over billions of years. Understanding how the cosmic web formed is one of the great achievements of modern cosmology. In the beginning, just after the Big Bang, matter was distributed almost perfectly uniformly throughout the young cosmos. Almost, but not quite. There were tiny density fluctuations. Some regions were slightly denser than average, containing perhaps 1 part in 100,000 more matter. Other regions were slightly less dense, containing 1 part in 100,000 less. These fluctuations were incredibly small. If you could have measured the density of matter in the early universe, you would have found it essentially uniform. The variations were so subtle that detecting them required measuring the cosmic microwave background radiation with extraordinary precision. But those tiny fluctuations were seeds. Seeds that gravity would cultivate over billions of years into the vast structures we see today. Gravity is an attractive force. Matter pulls on other matter. Regions that were slightly denser than average had slightly more gravitational pull. They attracted matter from their surroundings, becoming even denser. As they became denser, their gravitational pull increased, pulling in still more matter from the less dense regions nearby. Meanwhile, the less dense regions lost matter to their neighbors. They became even less dense, even emptier. With less matter, they had less gravity, making it even easier for neighboring dense regions to steal their remaining contents. This process is called gravitational instability, and it's a runaway effect. Small differences grow into large differences. Tiny fluctuations amplify into vast structures. Over billions of years, the nearly uniform early universe evolved into the highly structured cosmic web we observe today. The dense regions became the filaments and walls and clusters. The underdense regions became the voids. The primordial fluctuations, those 1 part in 100,000 variations in the infant cosmos, grew and grew until they became structures spanning hundreds of millions of light years. When we look at the cosmic web, we're seeing the growth of those ancient seeds. The pattern of filaments and voids encodes information about the very early universe. By studying the cosmic web, cosmologists can learn about conditions that existed when the cosmos was less than 400,000 years old. Computer simulations of this process have been remarkably successful. Scientists program in the conditions of the early universe the density fluctuations we observe in the cosmic microwave background, and then let gravity act over simulated cosmic time. The resulting virtual universes look remarkably like the actual cosmos. They develop filaments and walls and voids in patterns that match what our surveys reveal. This is one of the great triumphs of modern cosmology. We understand why the universe looks the way it does. The cosmic web isn't random or mysterious. It's the inevitable result of gravity acting on small initial variations over billions of years. Let me describe some specific features of the cosmic web to give you a sense of its staggering scale. The Sloan Great Wall, discovered in 2003, is one of the largest known structures in the universe. This cosmic wall of galaxies stretches approximately 1.37 billion light-years across. That's about 13,700 times the diameter of our entire Milky Way galaxy. Light would need more than 1 billion years to travel from one end of the structure to the other. Think about that. A structure so large that light, traveling at 186,000 miles per second, needs over 1 billion years to cross it. When the light now leaving one end of the Sloan Great Wall began its journey, complex multicellular life on Earth was just beginning to appear. By the time that light reaches the other end, Earth will have changed beyond recognition, if it still exists at all. The Hercules Corona Borealis Great Wall, first identified in 2013, may be even larger. Some estimates suggest it could be approximately 10 billion light-years across, though its exact boundaries are difficult to determine because it's so enormous and so distant. If confirmed at this size, it would be the largest known structure in the entire observable universe. 10 billion light-years. The universe itself is only about 13.8 billion years old. Light crossing this structure would have spent most of cosmic history making the journey. These walls aren't solid structures, of course. They're statistical concentrations, regions where galaxies are more common than average. But their sheer size is mind-bending. Structures spanning billions of light years, far larger than any galaxy, larger than any galaxy cluster, larger than any supercluster. These are the biggest things that exist. On the opposite extreme are the filaments, which can be quite thin relative to their enormous length. A typical filament might be only a few million light years in diameter, while extending for hundreds of millions of light years. These are the threads connecting the cosmic web, channeling matter from the empty voids into the dense nodes where clusters form. Imagine a thread, proportionally speaking, thinner than a human hair, but longer than a football field. That gives you a sense of how elongated these filaments are. They stretch across the cosmos like impossibly thin bridges, carrying galaxies along their length toward distant intersections. The galaxy clusters at the nodes of the cosmic web are themselves remarkable concentrations. The Virgo cluster, the nearest large cluster to us at about 54 million light-years away, contains approximately 1,300 galaxies. These galaxies orbit their common center of mass, bound together by gravity despite the universe's expansion. The Coma cluster, located about 330 million light-years from Earth, contains over 1,000 galaxies packed into a region, just 20 million light-years across. That's a lot of galaxies in a relatively small space by cosmic standards. The Coma cluster is one of the densest concentrations of matter in the nearby universe. And then there are superclusters, collections of clusters bound together into even larger structures. Our own supercluster, Laniakea, was defined in 2014 by astronomer Brent Tully and his colleagues. Laniakea contains about 100,000 galaxies spread across roughly 520 million light-years. 100,000 galaxies. The Milky Way, our home galaxy with its hundreds of billions of stars, is just one of these 100,000. One small piece of a supercluster, one node in the cosmic web, one grain of sand on a cosmic beach. But here's what's crucial to remember even as we discuss these massive structures. The cosmic web, impressive as it is still mostly nothing. Let's think about this carefully. The filaments where galaxies concentrate are denser than the voids, but how much denser? Studies of the cosmic web suggest that the typical density contrast between filaments and voids is about 10:1. Filaments are roughly 10 times denser than the surrounding voids. That sounds like a significant difference, and in relative terms, it is, but in absolute terms, in actual numbers of atoms per volume, both filaments and voids are extraordinarily empty. The average density of matter in the universe, if you spread all visible matter uniformly throughout all space, is about 6 hydrogen atoms per cubic meter. 6 atoms in a volume roughly the size of a small refrigerator. That's the cosmic average. Filaments, being denser than average, might have 60 atoms per cubic meter. Voids, being less dense, might have 1 atom per cubic meter or even less. In either case, we're talking about almost perfect emptiness. The difference between filaments and voids is the difference between almost nothing and even more almost nothing. From a human perspective, both are essentially vacuum. And remember, these densities are averaged over enormous volumes. Within a filament, most of the matter is concentrated in galaxies. Between the galaxies, even within a filament, the intergalactic medium is extraordinarily thin. A cubic meter of intergalactic space, even in the densest part of a filament, might contain only a single lonely atom. So when we talk about the cosmic web as a structure of matter, we need to maintain perspective. Yes, matter is organized into this beautiful web-like pattern. Yes, there are regions of relative density and regions of relative emptiness. But the dense regions are still almost entirely void, and the sparse regions are emptier still. The cosmic web is a structure of relative density, not absolute fullness. It's the pattern that near nothingness makes when gravity has been pulling on it for 13.8 billion years. Let me try another way to convey this. Imagine you took all the visible matter in the observable universe, every star, every planet, every cloud of gas, every grain of cosmic dust and spread it out uniformly across all space, how dense would this universal matter be? About 6 atoms per cubic meter. That's all. The entire visible contents of the observable universe, if distributed evenly, would give you 6 atoms in every cubic meter of space. Now, in reality, matter isn't distributed evenly. It's clumped into stars and planets and galaxies and clusters, all arranged in the cosmic web. So some regions are much denser than 6 atoms per cubic meter. The air you're breathing contains about 27 billion atoms per cubic meter. Your body is denser still. The rock beneath your feet is denser yet. But these dense regions, the places where matter has actually accumulated into tangible form, occupy only a vanishingly small fraction of the universe's volume. When you average over cosmic scales, the universe contains almost nothing. The cosmic web is important not because it contains a lot of matter, but because it shows us how the little matter that exists is organized. It reveals the architecture of the cosmos, the blueprint that gravity has been building for billions of years. And that architecture tells us something profound. The universe has history. The structures we see today didn't always exist. They grew from tiny seeds over cosmic time. The pattern of the cosmic web encodes information about the early universe, about the fundamental physics that governs reality. When cosmologists study the cosmic web, they're not just cataloging where galaxies are. They're reading the universe's autobiography. Every filament, every void, every cluster tells part of the story of how the cosmos evolved from a hot, dense, nearly uniform beginning to the complex, structured, but still overwhelmingly empty universe we observe today. This cosmic web also raises profound questions about our place in the universe. Where exactly do we fit in this vast architecture? We live in the Milky Way galaxy, which is part of the local group, which sits on the outskirts of the Virgo supercluster, which is itself part of the larger Laniakea supercluster. We're embedded in a filament of the cosmic web, a relatively dense thread in the overall structure. But we're also located near the edge of the KBC void, one of the largest underdense regions in our cosmic neighborhood. We're not in the densest part of the universe. We're not in the emptiest part either. We're somewhere in between, in a location that's unremarkable by cosmic standards. This is both humbling and reassuring. Humbling because it shows we're not at the center of anything. The universe has no center, and even if it did, we certainly wouldn't be there. We're just inhabitants of one galaxy among hundreds of billions, located in an ordinary part of an ordinary filament in an unremarkable region of the cosmic web. But it's also reassuring because it suggests our location is typical. We're not in some special place that might have unusual properties. We're in a normal region of a normal galaxy in a normal part of the cosmos. What we observe locally should apply broadly. This ordinariness is actually crucial for cosmology. It's called the Copernican principle, named after Nicholas Copernicus, who showed that Earth wasn't at the center of the solar system. The Copernican principle assumes that we don't occupy a special place in the universe. If our location were unusual, our observations might not be representative of the cosmos as a whole. But because we appear to be in a typical location, we can reasonably assume that what we see locally applies universally. The cosmic web extends across the entire observable universe. Everywhere we look, in every direction, at every distance our telescopes can probe, we see the same pattern. Filaments, walls, clusters, and voids. The Specific structures differ from region to region, but the overall character is consistent. This uniformity is itself a profound discovery. The universe looks roughly the same in every direction and at every distance we can observe. On the larger scales, it's homogeneous and isotropic, and the same everywhere and in every direction. The cosmic web, despite its complex local structure, averages out to uniformity when viewed across the entire cosmos. This uniformity was one of the original motivations for the Big Bang Theory. If the universe started from an extremely hot, dense state and expanded in all directions, you would expect it to look the same everywhere. And that's exactly what we observe. The cosmic web, the cosmic microwave background radiation, the distribution of matter on the larger scales, all point to a universe that began in a uniform state and has been expanding and cooling ever since. The cosmic web is also made of more than meets the eye. When we map the positions of galaxies, we're only seeing the visible matter, the stars and gas that emit or absorb light. But there's another component to the cosmic web, one that outweighs the visible matter by a factor of about 5-1. Dark matter. Dark matter is a form of matter that doesn't interact with light. It doesn't emit it, doesn't absorb it, doesn't reflect it. We can't see it directly with any telescope, but we know it's there because of its gravitational effects. Galaxies rotate faster than they should if they only contained visible matter. Galaxy clusters hold together more tightly than visible matter alone could explain. The cosmic web itself has a structure that requires more mass than we can see. All of these observations point to the existence of invisible matter, matter that has gravity but doesn't interact with the electromagnetic radiation. The cosmic web is primarily a web of dark matter. The dark matter forms the scaffolding, the underlying structure. Visible matter, the stars and gas we can actually observe, falls into this scaffolding, collecting in the densest regions where it forms galaxies and clusters. Think of it this way. If the cosmic web were a city, the dark matter would be the infrastructure, the roads and power lines and water pipes. The visible matter would be the buildings and people and vehicles, the stuff you actually see. But the infrastructure came first and determines where everything else goes. Computer simulations that include dark matter reproduce the cosmic web structure beautifully. Without dark matter, the simulations don't work. The universe would look different, with structures forming more slowly and on different scales. The fact that our simulations match reality when we include dark matter is strong evidence that dark matter is real, even though we've never directly detected a dark matter particle. So when we talk about the cosmic web, we're really talking about a structure that's mostly invisible. The galaxies we map are tracers, visible markers of an underlying dark matter skeleton that we can't directly see. The true architecture of the cosmos is hidden, revealed only through its gravitational effects. This adds another layer to our understanding of cosmic emptiness. The universe isn't just empty of visible matter. It's empty of dark matter too, except in the filaments and nodes of the cosmic web. The voids are empty of both kinds of matter. They're truly, profoundly void. The story of the cosmic web is still unfolding. The universe continues to evolve. Voids are still expanding. Filaments are still stretching. Galaxies are still falling toward clusters, channeled along the threads of the web toward the dense nodes where they'll merge with other galaxies. We're observing this process in action. We can see galaxies flowing along filaments, their motions betraying the gravitational pull of distant clusters. We can see clusters growing as they consume the matter flowing into them. The cosmic web is a work in progress, and we're fortunate enough to observe it at this particular moment in cosmic history. But the future of the cosmic web is already determined by forces we can observe today. The universe is expanding, and that expansion is accelerating, driven by a mysterious force called dark energy. Over billions of years, this acceleration will tear the cosmic web apart. Filaments will stretch and thin as space expands between their component galaxies. The threads connecting distant clusters will break as the expansion overcomes gravity. Clusters will become isolated islands, cut off from the cosmic web that once fed them. Eventually, trillions of years from now, the cosmic web will dissolve entirely. Each isolated cluster or galaxy group will exist alone in an expanding sea of emptiness. The intricate architecture we observe today will be nothing but a memory, or less than a memory, a fact that no intelligence might survive to recall. The cosmic web, this beautiful structure of matter, organized by gravity over billions of years, is temporary. It exists now in this epoch of cosmic history, but it won't exist forever. The universe began in uniform chaos and will end in scattered isolation. The cosmic web is the middle chapter, the brief period when matter was organized into patterns before being torn apart by expansion. We live during this middle chapter. We can observe the cosmic web, map its filaments and voids, trace its history back to the primordial fluctuations that seeded it. We can watch it evolve in real time as galaxies flow along filaments and clusters grow at nodes. This is a privilege. Future intelligent beings, if any exist in the distant epochs to come, will see only darkness beyond their local cluster. They won't be able to observe the cosmic web because it will have dissolved. They won't be able to deduce its former existence because all evidence will have been carried away by expansion. Only beings living in this cosmic era, this brief window of billions of years when the web still exists, can know its architecture. We are among those beings. The cosmic web is our heritage, our cosmic home, the structure in which we find ourselves embedded. And what a structure it is. A web of near nothingness, stretched across billions of light years. Filaments and walls and clusters arranged in patterns that trace back to quantum fluctuations in the infant universe. Dark matter forming an invisible skeleton with visible matter draped across it like lights on a Christmas tree. Voids expanding, filaments stretching, clusters growing, all in slow motion across cosmic time. The cosmic web is the architecture of emptiness, the shape that almost nothing makes when gravity has 13.8 billion years to work with. It's beautiful, it's vast, it's intricate, and it's almost entirely void. That's perhaps the most remarkable thing about the cosmic web. It's a structure made mostly of emptiness, organized into patterns of density and sparseness, where even the densest regions are nearly vacuumed by any human standard. The cosmic web reveals that even when the universe organizes itself, even when matter gathers into vast structures spanning billions of light years, emptiness still dominates. The voids are still there, filling 80% of the volume. The filaments are still sparse, containing mere atoms per cubic meter. Structure and emptiness aren't opposites. In the cosmos, structure is made of emptiness. The cosmic web is the shape of the void, the architecture of almost nothing, the pattern that near nothingness makes when it has an eternity to arrange itself. And in that almost nothing, we exist. Embedded in a filament of the cosmic web, orbiting a star in a galaxy, in a cluster, in a supercluster. One small node of matter in a universe that is overwhelmingly, fundamentally, beautifully empty. Now let's bring everything together. We've journeyed from the smallest scales to the largest, from atoms to the cosmic web, from the space within matter to the voids between superclusters. At every level, at every magnification, we've discovered the same fundamental truth. The universe is almost entirely nothing. Let me summarize the picture we've built, scale by scale, so you can hold the complete vision in your mind. Start at the smallest level. Atoms, the building blocks of everything you see and touch and experience, are approximately 99.9999999999999% empty space. The nucleus, containing almost all the atom's mass, occupies roughly 1/1,000,000th of the atom's volume. If you removed all the empty space from the atoms in a human body, the remaining matter would be smaller than a grain of salt. If you compressed all 8 billion humans on Earth, removing the emptiness within our atoms, the result would fit inside a single sugar cube. The solid world you experience, the table beneath your hand, the ground beneath your feet, the body you inhabit, all of it is overwhelmingly void. Solidity is an illusion created by electromagnetic forces, not by matter actually touching matter. You have never truly touched anything in your entire life. The electrons in your atoms repel the electrons in everything else, creating the sensation of contact across a gap of emptiness. Scale up to planets. Earth seems massive, a sphere nearly 8,000 miles across with a mass of 6 trillion kilograms. But Earth floats in emptiness. The distance to the Moon, our nearest neighbor, could swallow every other planet in the solar system lined up side by side. That gap of 238,000 miles is pure void. Absolute nothing separating us from the closest natural object in space. Scale up to the solar system. If the sun were a basketball, Earth would be a peppercorn 98 feet away. Jupiter would be a marble 500 feet distant. Neptune would be another marble over half a mile from our basketball sun. The entire solar system, including the distant Oort cloud, would span about 6,000 miles in this model, roughly the distance from New York to Tokyo. And within that enormous volume, the actual matter consists of one basketball, a few marbles, some peppercorns, and scattered specks of dust. Everything else is emptiness. The solar system is approximately 99.999999999999999% empty space. The matter within it, including our massive sun, occupies a fraction of the total volume so small that writing out all the zeros would fill this page. Scale up to the space between stars. If the sun were a marble half an inch across, the nearest star, Proxima Centauri, would be another small ball over 200 miles away. 200 miles of absolute nothing between half-inch spheres. The interstellar medium, the gas and dust scattered between stars, contains approximately 1 atom per cubic centimeter. That's 100,000 times emptier than the best vacuum we can create in any laboratory on Earth. Scale up to galaxies. The Milky Way contains somewhere between 100 billion and 400 billion stars. That sounds like an enormous number, and it is. But those stars are scattered across 100,000 light years of space. Even with hundreds of billions of stars, the galaxy is overwhelmingly empty. Matter occupies roughly 1 part in 10 to the 37th power of the galaxy's volume. The Milky Way is emptiness punctuated by occasional, isolated specks of light. Scale up to intergalactic space. The void between galaxies contains approximately 1 atom per cubic meter. That's 1 million times emptier than the already incredibly empty space within our galaxy. If you floated in intergalactic space, the nearest atom might be a meter away. The nearest star might be millions of light years distant. You would experience loneliness beyond human comprehension. Scale up to cosmic voids. The Boulter's void spans 330 million light years and contains only about 60 galaxies. The KBC void stretches roughly 2 billion light years across. These vast regions, occupying about 80% of the universe's total volume, are the true deserts of existence. Almost nothing exists within them. They are emptiness on a scale that language struggles to convey. Scale up to the cosmic web itself. Even the filaments and walls where galaxies congregate, the densest large-scale structures in the universe, contain only about 60 atoms per cubic meter on average. The cosmic web is a pattern of relative density, not absolute fullness. It's the shape that near nothingness makes when gravity has been working on it for 13.8 billion years. And finally, consider the average. If you took all the visible matter in the observable universe, every star, every planet, every cloud of gas, every grain of dust, and spread it uniformly throughout all space, you would get approximately 6 atoms per cubic meter. 6 atoms in a volume you could wave your hand through. That's the cosmic average. That's what the universe contains when you smooth out all its structure. This is the true picture. A cosmos where matter is the rare exception, where emptiness is the overwhelming rule, where the vast majority of existence is nothing at all. And yet, when you look up at the night sky, this isn't what you see. You see thousands of stars scattered across the darkness. You see the Milky Way stretching from horizon to horizon like a river of light. You see what appears to be a universe full of matter, full of light, full of stuff. This is one of nature's greatest illusions. The night sky deceives you. It shows you the exceptions while hiding the rule. It presents the rare places where matter has congregated while concealing the overwhelming emptiness that dominates everywhere else. You are inside a galaxy, looking out at other stars within that same galaxy. You're in one of the denser regions of the cosmos, a cosmic city surrounded by a cosmic wilderness. From your vantage point, the universe looks populated, but your vantage point is profoundly unrepresentative. If you could see the true nature of space, you would see almost nothing. The stars would appear as tiny, isolated specks, separated by vast gulfs of darkness. The Milky Way would be a sparse scattering of points surrounded by unimaginable emptiness. And beyond our galaxy, you would perceive a cosmic web of almost nothing organized into patterns of even less nothing. The illusion of fullness is created by light. By the way, photons travel across the void to reach your eyes, making the distance seem near and the sparse seem dense. But the light itself reveals the truth if you know how to read it. Those photons traveled for years, for centuries, for millennia through almost perfect emptiness before arriving at your retina. The very fact that you can see distant stars proves how empty space is. If there were matter in the way, the light would be absorbed or scattered. The clarity of the night sky is evidence of the void through which starlight travels. What does all this emptiness mean? What are its implications for how we understand ourselves, our existence, our place in the cosmos? Let me explore several profound consequences of living in a universe that is mostly nothing. First and most fundamentally, the emptiness means we are incredibly, improbably here. Matter is rare. The fact that atoms exist at all, rather than empty space, is already remarkable. The fact that those atoms gather together into complex structures, into planets, into life, into conscious beings capable of contemplating their own existence, is extraordinary beyond measure. Consider the odds. Pick a random point anywhere in the observable universe, any point at all. What are the chances you would find yourself inside a galaxy? Very small. Most of the universe is intergalactic void. What are the chances you would be near a star? Even smaller. Most of even the galaxies is interstellar emptiness. What are the chances you would be on a planet? Smaller still. What are the chances you would be on a planet with liquid water, with an atmosphere, with the right conditions for life? We don't know that probability precisely, but it must be unimaginably tiny. And yet here you are, a conscious being made of matter that shouldn't exist in most places, thinking about the emptiness that surrounds you. Your existence is a statistical miracle in a universe of void. Every atom in your body was forged in the heart of a star that died billions of years ago. Those atoms were scattered across light years of empty space when that star exploded. They drifted through the void for millions of billions of years before being swept up into the cloud of gas and dust that formed our solar system. They became part of Earth, part of the oceans, part of the first living cells, and eventually, through an unbroken chain of life stretching back nearly 4 billion years, part of you. You are made of material that is cosmically precious. Your body is a collection of atoms that have participated in the universe's story since the beginning. The emptiness around us doesn't diminish this fact. It amplifies it. Against the backdrop of cosmic void, your existence becomes all the more remarkable. Second, the emptiness puts our concerns in perspective. Every worry you have ever had, every conflict between nations, every struggle for resources, every triumph and tragedy in human history, all of it takes place on one small planet, orbiting one ordinary star in one galaxy among trillions. Surrounded by emptiness so vast the description fails. The arguments we have, the borders we draw, the differences we fight over, all of it occurs on a pale blue dot suspended in a sunbeam, to borrow Carl Sagan's famous phrase. From a cosmic perspective, our conflicts are invisible, our planet is invisible, our entire galaxy is just one collection of stars, among hundreds of billions. This doesn't make our concerns meaningless. They matter to us, and that matters. Pain is real. Joy is real. Love and loss and hope and fear, all of it is real and important to the beings who experience it. But the cosmic perspective suggests a certain humility. The universe didn't arrange itself for our benefit. We're not the center of anything. We're tiny beings on a tiny world in a cosmos that is mostly nothing. When you're caught up in the stress of daily life, when problems seem overwhelming and insoluble, it can help to remember this. Step outside on a clear night. Look up at the stars. Remember that each of those points of light is a sun, possibly with planets of its own, and that the space between them is vast beyond imagining. Remember that you're looking at a tiny fraction of one galaxy among trillions in a universe that is almost entirely empty. Your problems are real, but they're also small, contained to one life on one planet in one moment of cosmic time. The universe stretches away in every direction, empty and silent and ancient. Your troubles occupy an infinitesimal portion of it. Third, the emptiness makes the matter more precious. Because matter is so rare, the matter that does exist becomes extraordinarily valuable. Every star is a beacon in an ocean of darkness. Every planet is an island in a void that stretches for light years. Every living thing is a miracle of organization in a cosmos that trends toward disorder. You are made of rare stuff. The atoms in your body, the carbon and oxygen and nitrogen and all the rest, were manufactured in stellar furnaces over billions of years. Those elements are not common in the universe. Most of the ordinary matter in the cosmos is hydrogen and helium, the simplest elements. The heavier elements that make up rocky planets and living things had to be created through nuclear fusion in stars and scattered through supernova explosions. The very substance of your body is cosmically uncommon. You are not made of the stuff that fills most of the universe. You are made of the rare products of stellar evolution, gathered together into an even rarer configuration that thinks and feels and wonders. The emptiness around us is what makes the fullness within us so remarkable. Matter is precious because it's rare. Life is precious because it's rarer still. Consciousness, the ability to perceive and understand the cosmos, may be the rarest thing of all. Fourth, the emptiness raises profound questions about the nature of existence itself. Why is there something rather than nothing? This is perhaps the oldest and deepest question in philosophy, and the universe's overwhelming emptiness makes it even more pointed. If the universe were full of matter, if stuff were everywhere, we might not think to ask why. Existence would seem natural, normal, expected. But the universe is almost entirely empty. Matter is a rare exception to the rule of void. This makes the existence of matter seem more puzzling, more in need of explanation. Why did the Big Bang produce matter at all? Why didn't it produce pure emptiness? A universe of radiation and void with no particles, no atoms, no structures. The laws of physics as we understand them could, in principle, allow for such a cosmos, but that's not what happened. Instead, the universe produced matter, and that matter organized itself over billions of years into stars and galaxies and planets and life. Physics can describe how matter behaves. It can explain how atoms form, how gravity pulls matter into clumps, how stars ignite and planets coalesce. But why matter exists at all, why there is something rather than nothing, remains mysterious. The emptiness surrounding us frames this question in stark terms. Something exists in a cosmos that could easily have been nothing. Why? Fifth, the emptiness has profound implications for the possibility of contacting other intelligent life. If there are other civilizations out there, other beings looking up at their own night skies and wondering if they're alone, the vast emptiness between stars makes contact extraordinarily difficult. The nearest star to our sun is about 4.24 light years away. A radio signal traveling at the speed of light, the fastest anything can travel, would take over 4 years to reach it. A reply would take another 4 years to return. Any conversation would span nearly a decade for each exchange. And that's the nearest star. Most stars in our galaxy are hundreds or thousands of light years distant. A message to a star 1,000 light years away would take 1,000 years to arrive. A reply would take another 1,000 years. You could send a greeting and your distant descendants, 100 generations later, might receive an answer. Physical travel is even more daunting. With our current technology, it would take tens of thousands of years to reach even the nearest star. Even with hypothetical future technology, traveling at a significant fraction of light speed, journeys between stars would take years or decades. Journeys between galaxies would take millions of years. The emptiness between stars is not just inconvenient, it may be an effectively uncrossable barrier. Civilizations might exist throughout the galaxy, scattered across the cosmic void like islands in an ocean, but they might never meet. They might never even detect each other across the vast distances. This is one possible solution to the Fermi paradox, the famous question of why we haven't detected any signals from alien civilizations, given the vast number of stars and the long history of the universe. Perhaps civilizations are common, but the emptiness keeps them apart. Each one arises alone, develops alone, wanders alone, and perhaps dies alone, never knowing that other minds existed under other stars. If this is true, it's both melancholy and profound. It would mean that consciousness flickers into existence in isolated pockets throughout the cosmos, each one an island of awareness in an ocean of void. Each civilization develops its own science, its own art, its own philosophy. Each one looks up at the stars and wonders, but the gulfs between them are too vast to cross. They remain forever separate, forever lonely, forever unaware of each other's existence. We might be one such island, looking out at a universe that contains other thinking beings, but unable to reach them or even detect them across the emptiness that separates us. This is a sobering thought, but it's also a call to cherish the connections we do have, here on this one small world where we've somehow found each other. Sixth, the emptiness tells us about the future of the cosmos. The universe is expanding, and that expansion is accelerating. Every day, the voids grow slightly larger. The filaments stretch slightly thinner. The distances between galaxy clusters increase by imperceptible but relentless increments. Over billions of years, this expansion will transform the universe. The cosmic web will stretch until it tears. The filaments connecting distant clusters will snap as space expands faster than gravity can hold them together. Clusters will become isolated islands, each one alone in an expanding sea of emptiness. Eventually, the expansion will carry distant galaxies beyond the cosmic horizon. Their light will no longer be able to reach us because space between us and them will be expanding faster than light can cross it. The observable universe will shrink. The night sky will darken. Any intelligent beings living in that distant future will look out at the cosmos and see only their own local group of galaxies, perhaps merged by then into a single elliptical galaxy. Beyond that, darkness. The universe will appear to contain only one galaxy surrounded by infinite void. The evidence that other galaxies ever existed will have been carried away by expansion, lost beyond the horizon forever. We live in a special time, a window of cosmic history when the universe still has visible structure, when galaxies can still see each other across the void, when the cosmic web still exists to be mapped and studied. Future civilizations, if any survive to that epoch, will not have this privilege. They will inherit a darker, lonelier, emptier cosmos. The emptiness we observe today is just the beginning. The universe is becoming emptier over time, and that trend will continue for trillions of years. Emptiness is not just the current state of the cosmos, it's the direction the cosmos is heading. The trajectory of everything is toward maximum emptiness, a state approaching as close to nothing as existence can reach, while still technically being something. But let me conclude with a different perspective, because the emptiness, vast and humbling as it is also beautiful. When you look up at the night sky, you're seeing light that has traveled through that emptiness to reach you. photons that departed distant stars years or centuries or millennia ago, crossing the void at the speed of light, finally arriving at this one tiny planet at this one moment in cosmic history, entering your eye and triggering the neurons that let you perceive them. That light traveled through almost nothing to reach you. It crossed light years of emptiness without being absorbed or scattered. The very emptiness of space is what allows the light to travel. If the universe were full of matter, if stuff were everywhere, light couldn't propagate. We would be blind to the cosmos. The emptiness is not just absence, it's also possibility. It's the medium through which information travels. It's the canvas on which the cosmic web is painted. It's the silence that lets us hear the music of the spheres. There's something profound about our situation. We're tiny beings made of rare matter, living on a rare world in a cosmos that is almost entirely void. The emptiness surrounds us at every scale. It's within our atoms. It's between our sun and its neighboring stars. It's throughout our galaxy. It's across the cosmic web that structures the universe. And yet, here we are, thinking, wondering, looking up at stars that are light years away and understanding what we're seeing. Consciousness has arisen in this universe of void, and that consciousness can perceive and appreciate and struggle to comprehend the emptiness in which it floats. This is remarkable. Against all odds, matter clumped together in ways that allowed life to emerge. That life evolved for billions of years until it produced beings capable of looking out at the cosmos and grasping their own insignificance and rarity. We are the universe contemplating itself, and what it contemplates is mostly nothing. But here's the beautiful paradox. The emptiness doesn't diminish us. In some ways, it elevates us. We are the exceptions to the rule of void. We are the rare places where something happens. We are matter that thinks, atoms that wonder, stardust that contemplates the stars from which it came. The cosmos is almost nothing, but we are something. And in a universe of emptiness, something is extraordinary. When you next look up at the night sky, remember what you've learned tonight. Those stars you see are incredibly far apart, separated by light years of near-perfect void. The galaxies beyond our own are divided by even vaster emptiness. The cosmic web that organizes all visible matter is itself mostly nothing. Emptiness dominates at every scale, from the quantum to the cosmic. But also remember that you are seeing it. Light from those distant suns has crossed the emptiness to reach you. Your mind, made of matter that is cosmically rare, can contemplate the void. You can know the emptiness and your own improbability within it. That knowledge, that awareness, is itself a kind of fullness. The universe is empty, profoundly, overwhelmingly, almost incomprehensibly empty. Matter is rare. Life is rarer. Conscious life that can understand its own cosmic situation may be the rarest phenomenon of all. But it exists. We exist. Here, on this one small world, orbiting one ordinary star, in one galaxy among trillions, surrounded by emptiness that stretches in every direction for billions of light years. We are the universe's way of knowing how empty it is. We are matter that has organized itself to the point where it can look around and recognize its own scarcity. And that recognition, that awareness, transforms the emptiness from mere absence into something more, something meaningful, something worth contemplating. Tonight, if the sky is clear, step outside, look up. Let your eyes adjust to the darkness until you can see the stars in their multitudes. Remember that between each point of light is vastness beyond imagining. Remember that you're witnessing one of nature's great illusions, the appearance of a crowded cosmos created by light traversing emptiness. But also remember that you're there, standing on a planet that shouldn't exist in most places, made of atoms forged in stars that died before Earth was born, alive, conscious, capable of wonder. That's not nothing. That's everything. The universe is almost entirely empty, but in the emptiness, there is us, rare and precious and temporary, but real. Something existing in a cosmos of almost nothing. And in the end, that might be the most remarkable fact of all. Sleep well tonight, knowing that you are part of something extraordinary, something improbable, something that exists against all odds in a universe dominated by void. You are matter that has learned to think about matter. You are emptiness that has somehow become aware of itself. The cosmos is vast and mostly nothing, but you are something. And that makes all the difference. Good night.